Carbon is an element. It is a nonmetal. The amount of carbon present in the Earth's crust and atmosphere is very small. All the living things, plants and animals, are made up of carbon-based compounds which are called organic compounds. The atomic number of carbon is 6, which means that a neutral atom of carbon contains 6 electrons. So, the electronic configuration of carbon is K and L shell is to 4. It is clear that carbon has 4 electrons in the outermost shell, L shell, of its atom. Since a carbon atom has 4 electrons in its outermost shell, so it should either lose 4 electrons or gain 4 electrons to achieve the inert gas electron configuration and become stable. Now, carbon atom is very small, due to which its outermost electrons are strongly held by the nucleus. So, it is not possible to remove 4 electrons from a carbon atom to give it the inert gas electron arrangement. It is also not possible to add as many as 4 electrons to a carbon atom due to energy considerations and acquire the inert gas configuration. It is obvious that the carbon atoms have to acquire the inert gas structure of 8 electrons in their outermost shell by the sharing of electrons. Since carbon atoms can achieve the inert gas electron arrangement only by the sharing of electrons, therefore, carbon always forms covalent bonds. Covalent bond. Such bonds which are formed by the sharing of an electron pair between two atoms are known as covalent bonds. Covalently bonded molecules are seen to have strong bonds within the molecule, but intermolecular forces are weak. This gives rise to the low melting and boiling points of these compounds. Since the electrons are shared between atoms and no charged particles are formed, such covalent compounds are generally poor conductors of electricity. Single covalent bond. The atomic number of hydrogen is 1. Hence, hydrogen has 1 electron in its K shell and it requires 1 more electron to fill the K shell. So two hydrogen atoms share their electrons to form a molecule of hydrogen. This allows each hydrogen atom to attain the electronic configuration of the nearest noble gas, helium, which has 2 electrons in its K shell. The shared pair of electrons is said to constitute a single covalent bond between the 2 hydrogen atoms. A single covalent bond is also represented by a line between the 2 atoms. Double covalent bond. Oxygen has 6 electrons in its L shell. The atomic number of oxygen is 8, and it requires 2 more electrons to complete its octet. So each atom of oxygen shares 2 electrons with another atom of oxygen to give us the structure. The 2 electrons contributed by each oxygen atom give rise to 2 shared pairs of electrons. This is said to constitute a double bond between the 2 atoms. Triple covalent bond. Nitrogen has the atomic number 7. What would be its electronic configuration and its combining capacity? In order to attain an octet, each nitrogen atom in a molecule of nitrogen contributes 3 electrons, giving rise to 3 shared pairs of electrons. This is said to constitute a triple bond between the 2 atoms. Organic compounds. The compounds of carbon are known as organic compounds. Apart from carbon, most of the organic compounds contain hydrogen and many organic compounds contain oxygen or other elements. So, most of the organic compounds are hydrocarbons, containing only carbon and hydrogen, or their derivatives. Some of the examples of organic compounds are methane, ethane, ethene, ethine, trichloromethane, ethanol, ethanol, ethanoic acid, and urea. Carbon compounds, or organic compounds, are covalent compounds having low melting points and boiling points. The low melting points and boiling points of the above carbon compounds show that the forces of attraction between their molecules are not very strong. So, they are covalent compounds. Most of the carbon compounds are non-conductors of electricity. This also shows that carbon compounds are covalent in nature. They do not contain ions. The two characteristic properties of carbon element which lead to the formation of a very large number of organic compounds or carbon compounds are catenation and tetravalency. Catenation. Carbon atoms can link with one another by means of covalent bonds to form long chains or rings of carbon atoms. The property of carbon element due to which its atoms can join with one another to form long carbon chains is called catenation. When carbon atoms combine with one another, three types of chains can be formed. These are straight chains, branched chains, closed chains or ring-type chains. Tetravalency. A carbon atom has 4 electrons in its outermost shell, so it requires 4 more electrons to achieve the stable 8-electron inert gas electron arrangement, which it gets by sharing. Since one carbon atom requires 4 electrons to achieve the 8-electron inert gas structure, therefore, the valency of carbon is 4. That is, carbon is tetravalent. Due to large valency of 4, a carbon atom can form covalent bonds with a number of carbon atoms as well as with a large number of other atoms such as hydrogen, oxygen, nitrogen, sulfur, chlorine, and many more atoms. This leads to the formation of a large number of organic compounds. Saturated hydrocarbons. A hydrocarbon in which the carbon atoms are connected by only single bonds is called a saturated hydrocarbon. Saturated hydrocarbons are also called alkanes. We can now say that an alkane is a hydrocarbon in which the carbon atoms are connected by only single covalent bonds. There are no double or triple bonds in an alkane. Thus, the hydrocarbons methane, ethane, propane and butane form a series of compounds known as alkanes. The general formula of saturated hydrocarbons or alkanes is CnH2n+2 where N is the number of carbon atoms in one molecule of the alkane. If an alkane has one carbon atom in its molecule, then N1, and its molecular formula will be CnH2 or CHFO. If an alkane has two carbon atoms in its molecule, then N2, and its molecular formula will be C2H2 or CTWO6. The saturated hydrocarbons, or alkanes, are chemically not very reactive. They are quite unreactive. Unsaturated hydrocarbons. A hydrocarbon in which the two carbon atoms are connected by a double bond or a triple bond is called an unsaturated hydrocarbon. Ethene and ethine are two important unsaturated hydrocarbons because ethene contains a double bond and ethine contains a triple bond between two carbon atoms. A double bond is formed by the sharing of two pairs of electrons between the two carbon atoms, whereas a triple bond is formed by the sharing of 3 electron pairs between two carbon atoms. The unsaturated hydrocarbons are obtained mostly from petroleum by a process called cracking. Unsaturated hydrocarbons are of two types. Those containing carbon-carbon double bonds, alkenes. Those containing carbon-carbon triple bonds, alkynes. Alkenes. An unsaturated hydrocarbon in which the two carbon atoms are connected by a double bond is called an alkene. Thus, alkenes contain a double bond between two carbon atoms, which is formed by the sharing of two electron pairs, or four electrons. That is, an alkene contains the group. Ethene and propene are two alkenes because they contain double bond between the two carbon atoms. Since an alkene has a double bond between two carbon atoms, it is obvious that the simplest alkene will have two carbon atoms in its molecule. There can be no alkene having only one carbon atom. The general formula of an alkene is CnH2n, where n is the number of carbon atoms in its one molecule. Alkynes. An unsaturated hydrocarbon in which the two carbon atoms are connected by a triple bond is called an alkyne. Thus, alkynes contain a triple bond between two carbon atoms, which is formed by the sharing of three electron pairs, or 6 electrons. That is, an alkyne contains the group. Ethine and propyne are alkynes because they contain a triple bond between two carbon atoms. Since an alkyne has a triple bond between two carbon atoms, it is obvious that the simplest alkyne will have two carbon atoms in its molecule. There can be no alkyne having only one carbon atom. The general formula of alkynes is CnH2n-2, where n is the number of carbon atoms in one molecule of the alkyne. The unsaturated hydrocarbons, having double bonds or triple bonds between the carbon atoms, are more reactive than saturated hydrocarbons. In other words, alkenes and alkynes are chemically more reactive than alkanes. Another point to be noted is that the valency of each carbon atom in an alkane or alkyne is just the same, which is 4. The alkane having two carbon atoms in its molecule is ethane. The alkene having two carbon atoms is ethene, whereas the alkyne having two carbon atoms is ethyne. Ethane, ethene and ethyne are covalent molecules which are formed by the sharing of electrons between various atoms. A saturated cyclic hydrocarbon is cyclohexane. The formula of cyclohexane is C6H12. A molecule of cyclohexane contains 6 carbon atoms arranged in a hexagonal ring with each carbon atom having 2 hydrogen atoms attached to it. We can see from the structure that the cyclohexane molecule has 6 carbon-carbon single bonds and 12 carbon-hydrogen single bonds. The electron dot structure of cyclohexane has been obtained by putting 2 electron dots in place of every single bond in its structural formula. This is because every single bond consists of 2 shared electrons between the atoms. The saturated cyclic hydrocarbons are called cycloalkanes. Cyclohexane is a cycloalkane having 6 carbon atoms in its molecule. We can also have cycloalkanes with less than 6 carbon atoms in the ring. Thus, the cycloalkane having 3 carbon atoms in the ring is called cyclopropane. The cycloalkane with 4 carbon atoms in the ring is called cyclobutane, whereas the cycloalkane having 5 carbon atoms in the ring is called cyclopentane. An unsaturated cyclic hydrocarbon is benzene. The formula of benzene is C6H6. A molecule of benzene is made up of 6 carbon atoms and 6 hydrogen atoms. We can see from the structure that a benzene molecule has 3 carbon-carbon double bonds and 3 carbon-carbon single bonds. It also has 6 carbon-hydrogen single bonds. The electron dot structure of benzene has been obtained by putting 2 electron dots in place of every single bond and 4 electron dots in place of every double bond in its structural formula. This is because a single bond consists of 2 shared electrons, whereas a double bond consists of 4 shared electrons between any 2 atoms. The unsaturated cyclic compounds like benzene are called aromatic compounds. Isomers. The organic compounds having the same molecular formula but different structures are known as isomers. In other words, the organic compounds having the same molecular formula but different arrangements of carbon atoms in them are known as isomers. Normal butane and isobutane are examples of isomers because they have the same molecular formula but different structures. Normal butane has a straight chain structure, whereas isobutane has a branched chain structure. Another point to be noted is that the IUPAC name of N-butane is butane and that of isobutane is 2-methylpropane. Functional groups. A saturated hydrocarbon is unreactive, but if we introduce some other atom or group of atoms into it, the resulting compound becomes very reactive. This other atom or group of atoms present in a carbon compound is known as a functional group. Thus, an atom or a group of atoms which makes a carbon compound or organic compound reactive and decides its properties or functions is called a functional group. The alcohol group, present in ethanol, is an example of a functional group. Some of the important functional groups present in organic compounds are halo group or halogeno group, alcohol group, aldehyde group, ketone group, carboxylic acid group, alkene group, and alkyne group. Halo group. The halo group can be chloro, bromo, or iodo, depending upon whether a chlorine, bromine, or iodine atom is linked to a carbon atom of the organic compound. Chloro group is present in chloromethane, bromo group is present in bromomethane, and iodo group is present in iodomethane. Please note that the elements chlorine, bromine, and iodine are collectively known as halogens, so the chloro group, bromo group, and iodo group are called halo groups and represented by the general symbol X. So, we can say that the halo group is present in chloromethane, bromomethane, and iodomethane. Please note that halo group is also known as halogeno group. In fact, halo group is the short form of halogeno group. Halolcanes. When one hydrogen atom of an alkane is replaced by a halogen atom, we get halocane, also called halogenolcane. For example, when one hydrogen atom of methane is replaced by a chlorine atom, we get chloromethane. Alcohol group. The alcohol group is made up of one oxygen atom and one hydrogen atom joined together. The alcohol group is also known as alcoholic group or hydroxyl group. The compounds containing alcohol group are known as alcohols. The examples of compounds containing alcohol group are methanol and ethanol. Alcohols. Alcohols are the organic compounds containing hydroxyl group attached to a carbon atom. The hydroxyl group is the functional group of alcohols. The hydroxyl group attached to a carbon atom is known as alcohol group. The two simple alcohols are methyl alcohol, which is also known as methanol, and ethyl alcohol, which is also called ethanol. An alcohol is actually a hydroxy derivative of an alkane. So, an alcohol can be supposed to be derived by the replacement of one hydrogen atom of an alkane by a hydroxyl group. Aldehyde group. The aldehyde group consists of one carbon atom, one hydrogen atom and one oxygen atom joined together. Though the oxygen atom of the aldehyde group is attached to the carbon atom, but for the sake of convenience in writing, the aldehyde group is written as CHO with hydrogen atom in between the carbon and oxygen atoms. The carbon atom of the aldehyde group is attached to either a hydrogen atom or an alkyl group. The aldehyde group is sometimes called aldehydic group. The compounds containing aldehyde group are known as aldehydes. The examples of compounds containing an aldehyde group are methanol and ethanol. An aldehyde group always occurs at the end of a carbon chain. The carbon atom of the aldehyde group is attached to only one alkyl group. Aldehydes. Aldehydes are the carbon compounds, or organic compounds, containing an aldehyde group attached to a carbon atom. The two simple aldehydes are formaldehyde, which is also called methanol, and acetaldehyde, which is also called ethanol. Ketone group. The ketone group consists of one carbon atom and one oxygen atom. The oxygen atom of the ketone group is joined to the carbon atom by a double bond. The carbon atom of the ketone group is attached to two alkyl groups, which may be same or different. The ketone group is sometimes called a ketonic group. The compounds containing ketone group are known as ketones. The examples of compounds containing ketone group are propanone and butanone. A ketone group can occur only in the middle of a carbon chain, in between two alkyl groups. For example, in propanone, the ketone group occurs in the middle of the carbon chain, in between the two CH3 groups. A ketone group can never occur at the end of a carbon chain, because it has two free valences which have to be satisfied by two alkyl groups. Carboxylic acid group. The carbon compounds, or organic compounds, containing carboxylic acid group are called carboxylic acids. Carboxylic acids are commonly known as organic acids. Another name for carboxylic acids is alkanoic acids. The carboxylic acids or organic acids are made up of three elements: carbon, hydrogen, and oxygen. The simplest carboxylic acid, or organic acid, is formic acid, which is also known as methanoic acid. The most common carboxylic acid, or organic acid, is, however, acetic acid. Chemical properties of carbon compounds. The chemical properties which we are going to study here are combustion reactions, substitution reactions, and addition reactions. Combustion reactions occur in all types of hydrocarbons, saturated as well as unsaturated. Substitution reactions are given by only saturated hydrocarbons, or alkanes, whereas addition reactions are given by only unsaturated hydrocarbons, alkenes and alkynes. Let us start with combustion. Combustion. The process of burning of a carbon compound in air to give carbon dioxide, water, heat and light is known as combustion. Combustion is also called burning. Most of the carbon compounds burn in air to produce a lot of heat. For example, alkanes burn in air to produce a lot of heat, due to which alkanes are excellent fuels. When methane, natural gas, burns in a sufficient supply of air, then carbon dioxide and water vapor are formed, and a lot of heat is also produced. Since natural gas, methane, produces a lot of heat on burning, so it is used as a fuel in homes, transport, and in industry. The cooking gas, LPG, which we use in our homes, is mainly an alkane called butane. When butane, or LPG, burns in air in the burner of a gas stove, then it forms carbon dioxide and water vapor, with the evolution of a lot of heat and some light. Due to this, butane, or LPG, is an excellent fuel. The unsaturated hydrocarbons, alkenes and alkynes, burn in air with a yellow, sooty flame, producing black smoke. The unsaturated hydrocarbons, alkenes and alkynes, burn with a sooty flame because the percentage of carbon in unsaturated hydrocarbons is comparatively higher, which does not get oxidized completely in the oxygen of air. Substitution reactions. The reaction in which one or more hydrogen atoms of a hydrocarbon are replaced by some other atoms, like chlorine, is called a substitution reaction. If the substitution of hydrogen atoms takes place by chlorine, it is also called chlorination. Please note that substitution reactions, like chlorination, are a characteristic property of saturated hydrocarbons or alkanes. Unsaturated hydrocarbons do not give substitution reactions with halogens, they give addition reactions. The substitution reactions of saturated hydrocarbons, alkanes, with chlorine take place in the presence of sunlight. We will now give the substitution reaction of methane with chlorine. Substitution reaction of methane with chlorine. Methane reacts with chlorine in the presence of sunlight to form chloromethane and hydrogen chloride. In the above reaction between methane and chlorine, only one hydrogen atom of methane has been replaced by chlorine atom and we get chloromethane, CH3Cl, by supplying more chlorine. It is possible to replace all the hydrogen atoms of methane by chlorine, one by one. Addition reactions. The reaction in which an unsaturated hydrocarbon combines with another substance to give a single product is called an addition reaction. Addition reactions, like the addition of hydrogen, chlorine or bromine, are a characteristic property of unsaturated hydrocarbons. Addition reactions are given by all unsaturated hydrocarbons containing a double bond or a triple bond. That is, addition reactions are given by all the alkenes and alkynes. Ethene reacts with hydrogen when heated in the presence of nickel catalyst to form ethane. Unsaturated hydrocarbons add on hydrogen in the presence of catalysts such as nickel or palladium to form saturated hydrocarbons. The addition of hydrogen to an unsaturated hydrocarbon to obtain a saturated hydrocarbon is called hydrogenation. The process of hydrogenation takes place in the presence of nickel or palladium metals as catalyst. The process of hydrogenation has an important industrial application. It is used to prepare vegetable ghee or vanaspati ghee from vegetable oils. Some important carbon compounds. Ethanol or ethyl alcohol. Ethanol is a colorless liquid having a pleasant smell and a burning taste. Ethanol is a volatile liquid having a low boiling point of 78 degrees Celsius. It is lighter than water. Ethanol mixes with water in any proportion. The solubility of ethanol in water is due to the presence of hydroxyl group in it. Ethanol containing 5% water is called rectified spirit. Rectified spirit is the commercial alcohol. 100% pure ethanol is called absolute alcohol. Ethanol is a covalent compound. Ethanol does not contain any hydrogen ions, so it is a neutral compound. Thus, ethanol has no effect on any litmus solution. Chemical properties of ethanol. Reaction with sodium metal. Ethanol reacts with sodium to form sodium ethoxide and hydrogen gas. This reaction is used as a test for ethanol. When a small piece of sodium metal is put into ethanol in a dry test tube, rapid effervescence due to the evolution of hydrogen gas is produced. The hydrogen gas produced can be tested by burning. When a burning splinter is brought near the mouth of the test tube, the gas burns with a pop sound, which is a characteristic of hydrogen gas. This shows that the gas produced by the action of sodium metal on ethanol is hydrogen. In fact, all the alcohols react with sodium metal to evolve hydrogen gas. Dehydration. Dehydration of an alcohol means removal of water molecule from it. When ethanol is heated with excess of concentrated sulfuric acid at 170 degrees Celsius, it gets dehydrated to form ethene, which is an unsaturated hydrocarbon. In this reaction, concentrated sulfuric acid acts as a dehydrating agent, which removes water molecule from the ethanol molecule. Ethanoic acid. Ethanoic acid is the second member of the homologous series of carboxylic acids, the first member being methanoic acid. The formula of ethanoic acid is CH3COOH. The common name of ethanoic acid is acetic acid. A dilute solution of ethanoic acid in water is called vinegar. Vinegar contains about 5 to 8% ethanoic acid. Ethanoic acid is a colorless liquid having a sour taste and a smell of vinegar. The boiling point of ethanoic acid is 118 degrees Celsius. When pure ethanoic acid is cooled, it freezes to form a colorless, ice-like solid, which looks like a glacier. Due to this, pure ethanoic acid is called glacial ethanoic acid or glacial acetic acid. Ethanoic acid is miscible with water in all proportions. Reaction with ethanoic acid, formation of ester. Ethanol reacts with ethanoic acid on warming in the presence of a few drops of concentrated sulfuric acid to form a sweet-smelling ester, ethyl ethanoate. The reaction in which a carboxylic acid combines with an alcohol to form an ester is called esterification. Esterification takes place in the presence of a catalyst like concentrated sulfuric acid. The above reaction is an example of esterification. The formation of sweet-smelling esters is used as a test for alcohols as well as carboxylic acids. We can carry out the reaction between ethanol and ethanoic acid to form an ester as follows. Take 1 ml of pure ethanol, absolute alcohol, in a test tube and add 1 ml of glacial ethanoic acid to it. Then add 2 or 3 drops of concentrated sulfuric acid to the mixture. Warm the test tube containing above reaction mixture in hot water bath, a beaker containing hot water, for about 5 minutes. Pour the contents of the test tube in about 50 ml of water taken in another beaker and smell it. A sweet smell is obtained indicating the formation of an ester. Chemical properties of ethanoic acid. Due to its acidic nature, ethanoic acid reacts with carbonates, hydrogen carbonates, and bases, or alkalis, to form salts. Reaction with sodium carbonate. Ethanoic acid reacts with sodium carbonate to form sodium ethanoate and carbon dioxide gas. When sodium carbonate is added to a solution of ethanoic acid, brisk effervescence of carbon dioxide is given off. The salt formed in this reaction is sodium ethanoate. The common name of sodium ethanoate is sodium acetate. All other carboxylic acids react with sodium carbonate in a similar way. Reaction with sodium hydrogen carbonate. Ethanoic acid reacts with sodium hydrogen carbonate to evolve brisk effervescence of carbon dioxide gas. This reaction is used as a test for ethanoic acid or acetic acid. In fact, all the carboxylic acids decompose sodium hydrogen carbonate, giving brisk effervescence of carbon dioxide gas. Reaction with sodium hydroxide. Ethanoic acid reacts with bases or alkalis to form salts and water. For example, ethanoic acid reacts with sodium hydroxide to form a salt called sodium ethanoate and water. In its reaction with bases, ethanoic acid behaves just like mineral acids, HCl, etc. In fact, all the carboxylic acids react with bases or alkalis like sodium hydroxide to form the corresponding salts and water. Hydrolysis of esters. When an ester is heated with sodium hydroxide solution, then the ester gets hydrolyzed, breaks down, to form the parent alcohol and sodium salt of the carboxylic acid. For example, when ethyl ethanoate ester is boiled with sodium hydroxide solution, then sodium ethanoate and ethanol are produced. The alkaline hydrolysis of esters, using alkali like sodium hydroxide, is known as saponification, soap making. This is because of the fact that this reaction is used for the preparation of soaps. When the esters of higher fatty acids with glycerol, oils and fats are hydrolyzed with sodium hydroxide solution, we get sodium salts of higher fatty acids, which are called soaps.